When you look at a piece of AI-generated text, how do you know if you can trust it? With most AI chatbots today, you can look for three things: which model it's using, whether you see any thinking traces, and whether it references any external sources. But none of these really give you any guarantees. The best model can still hallucinate. Thinking traces, they might be fabricated. External sources, they can be wrong, or the citations are paraphrased incorrectly. You see, generic AI apps are essentially just a thin web UI wrapper around the underlying statistical model. What you see on screen is pretty much the raw text output coming right out of the model. There are no strict mechanisms for fact-checking, no guarantee of correctness. This simplicity makes the system cheap and flexible, easy to manage, and very general, good for general purpose use by the public. But that means it's not optimized for any specific high-stakes domains like health and nutrition. Now, what does it mean for the AI system to be optimized specifically for health? What kinds of domain specializations are possible? Specialization for health domain can happen in many parts of an AI system, beyond just being a simple wrapper of the LLM model. This Microsoft paper shows one example of how a health specialized system could look like. Specifically, this paper focuses on one way of specialization called test time scaling, which basically means they don't change the LLM model itself, only change the ways, the order, the flow that LLM models are used. We'll see what this means in a bit. And the result is an AI system that does the task of so-called sequential diagnosis and advances both diagnostic precision and cost effectiveness. Okay, so how does this work in practice? Let's walk through it. In this paper, again, they call the process a sequential diagnosis. The goal is simple: to make an accurate diagnosis by interacting with a patient. The input to the system is a short description of the patient's symptoms and conditions. The output is a final diagnosis. In between, the system runs through an iterative and structured process. Structured means there are constraints. The AI is restricted to one of the following three actions: asking follow-up questions, ordering relevant lab tests, and giving the patient a diagnosis. As a user, you start by describing why you are seeking care, your symptoms, how you're feeling, and some health history. Based on that, the system comes back with a follow-up question. It is basically a question based on your initial description, requesting for more information. It may ask for what's missing, what's relevant, what you might not have mentioned, etc. You provide the information, the system may ask a couple of more questions, then it may decide to order some tests. You provide results, and this loop continues until the system is ready to deliver a diagnosis. Now you might think like, okay, but generic AI chatbots can also ask follow-up questions, right? Yes, but here's the difference. What makes a system like this really powerful is not just what it does, but how it's designed, the structure behind it. First, the system has an explicit mechanism for identifying information gaps in the health domain. That means the AI is not just freely generating text however it wants. It's systematically probing for what is missing for making a diagnosis decision. Second, the system has an explicit mechanism for double-checking and making sure decisions are high quality on important metrics. Essentially, it comes down to two layers of structuredness imposed on the AI model throughout the system: the structure of the output format and the structure of the AI's flow of reasoning. For output structure, we force the model to produce specific types of outputs. For example, follow-up questions, requests for tests, final diagnosis. For flow structure, we force one or multiple AI models to generate outputs following a predefined order and flow. Let's look at output structure first. The default way to use AI is via a chatbot interface. AI outputs free text, very little restriction whatsoever. Here, instead of having the model output content in plain text of any format, a certain output structure is strictly imposed. In this case, to force the model to identify information gaps and ask questions back, order lab tests, or decide to finalize a diagnosis. Now, if you wonder if this is practical at all, how do you force an AI to output with structure? Remember, a language model is just predicting the next word, and it is actually possible to programmatically force the model to select a certain set of words instead of following its own prediction. In practice, doing so is actually getting easier than ever. Even APIs for closed source models now let developers constrain outputs with grammar rules or JSON schemas. This is one of the most powerful ways developers can tame AI models. Without enforced structures, output is massively dependent on how each model is trained. The style, taste, verbosity, helpfulness, etc. However, by forcing model output into a structure, you strip away the style and other quirks, and what's left is raw intelligence, which is largely what we want and what we need for performing a specialized task. The second structure, flow structure. In the case of this paper, to make decisions that are accurate and trustworthy, the system explicitly runs generation many times in a structured way. For instance, in this research, the authors define 5 roles for the AI and form a so-called virtual debate panel. Think of it like 5 doctors in the same room, each with a different personality, debating your case as a patient. Here you can see they have 5 different roles. Doctor Hypothesis, this is an AI that keeps track of all possible conditions. Doctor Test Chooser, it picks the most informative tests. Dr. Challenger, it plays devil's advocate, pushing back on assumptions. Dr. Stewardship, it balances cost and invasiveness. And Dr. Checklist, it makes sure nothing important gets skipped. Unlike a generic AI chatbot, which typically just runs a single LLM generation, a thing wrapper, here the system is running multiple generations with different roles. Each role has a distinct prompt and output format optimized for that specific responsibilities. By doing so, the system explicitly asks AI models to actively check and balance each other's reasoning and decision making. It forces the AI to critique itself, weigh costs, and avoid biases. In this paper, all roles were played by the same LLM, meaning an identical model is run multiple times in some order. But you could imagine defining roles differently, or even mixing models from different providers, since each model from different providers has different strengths and knowledge gaps. Combining them makes the system more robust. As mentioned before, this technique of making multiple AI calls instead of just one without changing the model itself is essentially a form of test time scaling for LLMs, and it is not new. It's been repeatedly shown to work well. xAI's Grok 4 has a mode to make multiple AI calls to conduct research to answer a question in parallel and merge the results finally. This Google research shows an improvement on a deep research system by having AI actively reflecting on knowledge gaps and revise answers. Now that we have 2 mechanisms to get high quality output from an AI doctor, there's one last ingredient to make the system truly trustworthy and usable in practice. What we have seen is 1, you need output structure, and 2nd, you need flow structure. And the final ingredient is the system should let the user know that you are doing the above too. Not just behind the scene, but the system has to show it on the user interface. Imagine at each step, you don't just get an answer, you also get a process log, so to speak. This is the key difference. The process log reveals in detail how the AI came up with the decision with the above mechanisms of forcing the model to follow certain structures. This process log is different from the thinking traces you see in a generic chatbot. The thinking traces, or more formally called chain of thought reasoning, are basically just the same old free text generation coming out of a single LLM with no constraints. Sure, the model may spontaneously decide to double check its previous generations, but it may not. You never know. In a system with explicit role-playing AIs, for example, if the system follows the debate panel structure above, there are explicit steps like Dr. Challenger, Dr. Checklist to double-check for biases and inconsistencies, and the user will easily see that the system is doing so every single time the user gets an output from the system. Such an UI is key to ensuring transparency because it lets the user understand how the system makes decisions and convince them that the output can be trusted even when it's based on LLMs, which can make mistakes. Again, the point is that it's important to show the user what happened under the hood. Model providers like OpenAI and xAI are likely already doing implicit improvements by asking AI models to follow structured flows. For example, training AI models in a way that makes them better work with each other, more willing to, and better at reflecting and correcting their own mistakes, etc. But these efforts are invisible. It's crucial that AI apps let users know in real time the kind of mechanisms and effort that's explicitly put into the system to improve quality. How many AI generations behind the scene were made? Were there any divisions in roles for multiple AI models, or identical AIs are doing the same work in parallel? What was the actual content of the debate, and how were answers merged? Regardless of how smart a single AI is, explicit multi-call setups are still needed, especially in health, because they give users transparency into what's happening behind the scene. Now, this paper actually consists of two parts. One is a system for the AI doctor, as we've already discussed. Another part is about a system for evaluating the AI doctor. In this video, the focus is on the actual AI doctor system, but just briefly, the paper built an evaluation system and claims that the AI doctor beats human doctors. There had been controversies and criticisms claiming the comparisons were unfair to human doctors, but that's not the real point. The authors need to somehow show the system is better to publish the paper as soon as possible. But even if today's numbers aren't perfect, even if they're fake, imagine what the performance of AI doctors will look like in 5 years. The raw intelligence of LLMs will get incremental improvements. Besides, what we are looking for is not AI replacing human doctors 100%. In essence, the AI model serves as a connective layer between the user's health conditions with two data sources. One is the information encoded in the model parameters, and the second is the databases the AI system has access to behind the scene. Given an AI, we want to extract its broad knowledge base and its ability to connect dots, and together these can augment and accelerate what human health providers do. So to summarize, what we have seen here is an application of AI not in the standard chatbot format. Instead of using LLMs as just chatbots generating free text, we force the models to output in a certain format, in a certain order, in a way that is tuned for the specific domain of health. And we make the process very explicit and open to the user. LLMs are malleable. We're just scratching the surface of what's possible. Such a way of shaping AI's output is possible today. As this paradigm is adopted more, the process may be injected into the training process of the model, directly tuning the model to perform even better following this format. There are still big elephants in the room. For example, data sources the system has access to and costs are the two major ones. Stay tuned for future videos for those topics.